Hello everyone, I'm James and welcome to the last episode of the OpenGL Tutorial Series. Today we're going to finish off the series with adding soft edges to our shadows. Let us go ahead and begin. This is how our shadows look right now. They are very pixelated. We can improve the shadow with linear filtering. This is how linear filtering looks. Achieving this result is very easy. All we need to do is interpolate between the previous pixel and the next pixel when sampling the depth map. Let's go ahead and start implementing it in our shader. The first thing I'm going to do is to move the sampling of the shadow map in a function. So I'm going to create a function that will return a float. It's going to be called sample shadow map. It's going to take in the shadow map itself. It's going to take in the x and y coordinates and the z coordinates, which I call current depth value. Now we'll move this code into here, and we'll change these as we need. So we'll use shadow map instead. We can pass in chords directly here, and instead of shadow map chords.z we use current depth value. And instead of doing light effect like this, we'll return 0, and in this case we'll return 1. Now in the main function we need to call this function, and what I'm going to do is I'm going to do light effect times equals sample shadow map, and we'll pass in the u shadow map. For the coordinates we'll pass in shadow map chords.xy, and for the current depth value we'll pass in shadow map chords.z. And if we run now, we should get the exact same result as before. And there you go, we get the exact same result. Now it's time to add linear filtering. We'll first start by adding a new function to sample the shadow map linearly. This will take the same parameters as the sample shadow map function. However, we need an additional parameter, which is the pixel size. The first thing we need to do is find the actual position in pixel space. All we need to do is divide the coordinates by the pixel size and add 0.5. Now we need the fractional part of the pixel position. This will give us the distance between the previous pixel and the current location. Now we need to get the position of the nearest pixel. We do this by subtracting the fractional part from the pixel position. We need the start pixel position in between 0 and 1, so we'll multiply it by pixel size. Now we need to sample the 4 surrounding pixels, and we'll use the sample shadow map function we created. Now we'll interpolate the bottom and top with the x component of the fractional part. Finally, we'll return the bottom and top interpolated with the y component of the fractional part. So now instead of calling sample shadow map, we'll call sample shadow map linear. However, we need the pixel size. To get the pixel size, we need the shadow map size. So we're going to add a new uniform for the shadow map size. Uniform, it's going to be a vec2 u shadow map size. And in the material, we're going to go in the material, the diffuse material, and we're going to send the shadow map size as a uniform. So u shadow map size is going to be shadow map arrow width, and we'll store this in a vec2. So glm vec2 shadow map width, and we'll add shadow map height for the y axis. There we go. So now to get the pixel size, all we have to do is 1 divided by U shadow map size. Let's see what happens if we run. And there you go. It's working perfectly. As you can see, the shadows look a little bit better. They're a bit smoother now. The pixels still show, however, and they're not very soft. But at least we have linear filtering. So the next target is to add soft shadows and make them actually soft with what's called percentage close filtering. So let's imagine this simple example. We have a shadow that is very simple. So this part is in shadow and this part is in light. The reason why I duplicated this is so that we can work on one image while still preserving the image without percentage close filtering. So how does this work? Well, it's actually very simple. So let's decide what color the first pixel, the pixel here is. So what color this pixel should be? Well, let's say we sample 3 by 3, so like this. So in this region, as you can see, all the pixels are in shadow. So this pixel here is going to be black. Let's try this pixel, and it's the same story, all in shadow, so we'll keep it as black. Now let's take this pixel. This pixel, as we can see here, or let's do this pixel first, because yeah, first this pixel, we've almost skipped it. But if we take a look at this, we now have 1/9 of 1/9 that is in light. So this pixel here needs to be 1/9. Now 1/9, well, we'll get out the calculator, or you won't see the calculator, but I'll get the calculator out quickly. 1 division by 9 is 11.1%. So here I'll pass in 11.1%. And that is going to be the color of the pixel. And did it work or not? Ah, no, it didn't work because we have a selection. Alright, so now if we do this, there we go. That is the color of that pixel. Now let's go to the next pixel. Now we have 3 pixels out of 9 that are in light. So that is basically 1/3. And 1/3 is 33.333 recurring percent. So let's make this 33.3, and we'll color this pixel as well, and we need to deselect as usual. So there we go, and that is going to be that pixel. I went ahead and did the same process for the rest. So to remind you again how the process works, we sample a square, so let's say this square, and in this case we have 1, 2, 3, 4, 5, 6 pixels and that are in light, and 3 pixels that are in shadow. So that is 6/9, and that is 2/3. And this is the final color we got. And I did it for every single pixel, and this is the nice result we get. As you can see, it's very smooth. You might not see it that smooth because we're zoomed in a lot, but if you had to zoom out, you would realize, well, it's very small, but you would realize that it's a nice smooth shadow, which is awesome. So let's go ahead and implement that in the shaders.
So we'll add a new function, this time to sample a shadow map with percentage close filtering. This will take in the same parameters as sample shadow map linear, however it will take an additional float parameter. This parameter will specify how many pixels to sample from the surrounding area. If we have 5 samples, we need to start sampling from -2 to +2, so we'll calculate how much samples there are on each side. I'll store the result in a float variable. We'll loop through the area of pixels. Next, we'll get the offsetted coordinates by multiplying the x and y variables by the pixel size. Next, we'll sample the shadow map and add the result to the result variable. Finally, we'll return the average result. The denominator is the sample area, so we'll do sample size times sample size.
Let us try using the sample shadow map PCF. Instead of sample shadow map linear, I'll pass in sample shadow map PCF, and we need that additional samples parameter, which I'm going to set to 3 for now. Let us see what happens if we run now. And there you go, look at that. The shadow is much softer now. Awesome. However, I think we can afford making it a little bit softer as well. And this is very easy to do now. All we have to do is increase the samples. Let's say we do 5. And now if we run, there you go, look at that. Look how soft the shadows are. Awesome.
And that, my friends, is the end of the OpenGL Tutorial Series. The code we written throughout the series isn't the ideal code you would use in a game engine, for example. I just wanted in a very quick manner to get a bunch of fancy effects with OpenGL, and hopefully you learned a lot of OpenGL concepts along the way. That was the purpose of the series. I hope you enjoyed the series, thanks a lot for watching, and goodbye.